Welcome to The Explainer. Today, we're diving into a full-blown cosmic mystery, the black hole information paradox. This is a story where our two best theories of the universe, general relativity and quantum mechanics, are in a total standoff, pointing fingers at each other. And the only witness? A black hole. So, to get to the bottom of this, we've got to start somewhere really weird, with a clue that seems like it has nothing to do with black holes at all. It all starts with a very simple question. What exactly is empty space? So back in 1976, a physicist named William Unruh comes up with this wild idea. He predicted that if you could accelerate through the vacuum of space fast enough, it wouldn't feel cold and empty. Nope, it would actually feel warm, like the vacuum itself was glowing with a faint heat. Okay, and this is where it starts to connect back to our black hole. Thanks to Einstein, we know a powerful secret about the universe. Extreme gravity feels exactly the same as extreme acceleration. So the Unruh effect has a very famous cousin, the Hawking effect. You just swap out the accelerating spaceship for the mind-bending gravity at the edge of a black hole. All right, so let's dig into this first clue, right? This whole heat from empty space thing. For almost 50 years, it was just a ghost in the equations, something purely theoretical. But that might be about to change, thanks to a potential breakthrough that was proposed just last year. So why haven't we just measured this? Well, here's the catch. To actually feel this heat, you would need to accelerate at a rate that is just impossible. It's so ridiculously fast, there's no way we could ever build anything like it in a lab. The signal is just way too quiet to hear. But then, in late 2023, a team of physicists proposed this incredibly clever workaround. Instead of trying to listen for that tiny whisper, they figured out a way to make it shout. The idea is to use a choir of atoms trapped between two mirrors. When you accelerate them, they should release a flash of light that's perfectly timed, a clean, loud signal of the Unruh effect. All right, so let's get back to the scene of the crime and see how this idea of heat coming from nowhere creates an even bigger puzzle. Just remember that key connection. Extreme acceleration is just like extreme gravity. You know, for the longest time, physicists thought of black holes as the ultimate prisons of the universe, a one-way street. Anything that crossed the event horizon, that point of no return, was gone for good, locked away forever. Information, matter, light, you name it. But then, in the 1970s, Stephen Hawking did something absolutely revolutionary. He took the strange rules of quantum mechanics and applied them to the edge of a black hole. And he realized that its insane gravity should make the vacuum around it glow with heat, just like the Unruh effect. And that meant black holes weren't completely black after all. So how does this work? Well, it gets into the weirdness of quantum physics. See, empty space isn't really empty. It's constantly fizzing with pairs of virtual particles that pop into existence and then disappear. But right on the edge of a black hole, one particle can fall in while its partner escapes. That escaped particle becomes real, and it has to steal a tiny bit of energy from the black hole to do it. We call this constant trickle of particles Hawking radiation. And here's the absolutely crucial part. If a black hole is constantly spitting out particles, it's losing energy. And since E equals mc squared, it's also losing mass. So over an almost unimaginable timescale, this slow leak means the black hole gets smaller and smaller until it evaporates completely, vanishing in a final burst of radiation. The fact that a black hole can just disappear? This is what leads us right into the heart of the mystery. If the black hole is gone and everything it ever swallowed is gone with it, what happens to the information that described all that stuff? I mean, really think about what that means. Every single particle that made up the star that collapsed, every asteroid or planet the black hole ever ate, all of it contained unique information. Its mass, its spin, where it was. If the black hole just evaporates into a bunch of random heat, where did all of that specific, detailed information go? And that, right there, is the information paradox. See, in quantum mechanics, there's a golden rule. You can't delete information from the universe, period. You can scramble it, you can hide it, you can rearrange it, but you can never, ever truly erase it. And yet, Hawking's calculations seem to show a black hole doing just that. And look, this isn't some small academic squabble. This is a full-blown crisis. It's a head-on collision between our two greatest theories of the universe. General relativity tells us a black hole has a smooth, drama-free event horizon. But quantum mechanics screams that the information about what falls in has to get out somehow. They literally can't both be right. So how in the world do you solve a crime like this? Well, over the years, physicists have put together a lineup of suspects, basically, a few possible scenarios, and each one is more radical than the last. Okay, so the first suspect, maybe the information really is just gone. That would mean we have to rewrite quantum mechanics from the ground up. The second idea is that maybe the black hole never fully evaporates. It leaves behind a tiny, super dense nugget containing all the information. That has its own weird problems. So most physicists today are betting on the third suspect, that somehow the information gets out. It's secretly encoded in the Hawking radiation itself. Now, for the information to escape, that radiation can't be random static, right? It has to be carrying a message. That means its information content, what physicists call its entropy, has to change over time. It should rise for the first half of the black hole's life, and then it has to start falling as the information begins to leak back out into the universe. That path is what we call the page curve. But, and there's always a but in this story, this beautiful solution creates a whole new monster. For the information to get out, the escaping particle has to be connected to the black hole's history. But quantum rules say it also has to be connected to its twin that fell in. It can't do both. If you force it to break that original link, you unleash a torrent of energy, turning Einstein's calm event horizon into a raging wall of fire. This is the firewall paradox. And this brings our whole detective story full circle. We're back where we started, with a paradox inside a paradox. Every time we think we have a solution, it just creates a new problem. So where do we find the next clue? Let's look at that experiment one more time. Remember the choir of atoms? By trapping them between mirrors, you get them to act in unison. When you accelerate the whole setup, that tiny bit of heat from the Unruh effect is like a conductor tapping a baton, telling the choir to sing their flash of light just a tiny fraction of a second earlier than they would have otherwise. It's that subtle shift in timing that lets you turn the whisper into a measurable shout. So you might be thinking, okay, cool experiment, but what does it really have to do with black holes? Well, everything. Because proving the Unruh effect isn't just about finding heat in a vacuum. It's about building the first real tools that can poke and prod at the bizarre physics where quantum mechanics and gravity collide. We're learning how to investigate a black hole's event horizon without leaving Earth. And that leaves us with this really incredible thought. For decades, we all assumed that the secrets of black holes could only be found by pointing bigger and better telescopes out at the cosmos. But maybe, just maybe, the key to solving one of the biggest mysteries in the universe isn't out there in space, but right here, in a lab, by finally figuring out how to turn a theoretical whisper into a shout.